All right, so we're going to now venture into a different section of the class, and it uses a different part of your brain. You know, the first section was mostly just kind of introductory definitions, some simple math skills, measurements, not really that much chemistry, a little bit, right? And then the last section was really a deep dive into the theory, right? We really didn't do much math. There was some, but the meat of that last section was really more theoretical, quantum theory, and how we use that to explain and use the periodic table, and also understand how electrons are arranged stably in an atom. And then that will help us understand what's coming next, why certain reactions happen the way they do, why are electrons lost or gained to become more stable. And now, as we're going to see in this chapter, what happens when they do lose or gain electrons to become more stable. They're going to end up and form ionic bonds. And we're also going to learn about covalent bonds, and then building models for us to understand what these compounds might actually look like if we could see them, but more importantly, how they behave in nature, how they behave chemically. So we'll be able to make some predictions at the end of this section about what's the overall shape of a compound and what are some of its properties. Is it polar or is it non-polar? Does it have a high boiling point? Things of that nature. But really, it's all about building more models and using those models to describe the kind of bonding that we think is taking place. Now, as we mentioned before, the chemical reactions that we study, right, those happen due to an interaction of just the valence electrons only. So only those electrons in the outermost shell. You all know what a valence electron is now. I hope you haven't forgotten it already. Right? And these valence electrons, they're going to rearrange to form a more stable configuration. It's all about stability in the end. We're trying to get most stable. And those valence electrons, they're either going to be lost or gained, or as we'll see soon enough, they'll be shared to give us a more stable configuration in the products. Now, you've already seen what happens when they're lost and gained. We did a little bit of that last chapter. We form positively charged cations and negatively charged anions. That gives us ions. The ions then will combine to form an ionic bond. And we'll look into that a little bit more detail today. When they're shared, as you'll see soon enough, when they're shared, that's going to form a covalent bond. And those are the two bonds that we're going to be studying in this chapter. But the bond itself is just a force of attraction between any two atoms, whether it's ionic or covalent. Okay, it's just an attractive force. And it involves only the valence electrons. Okay. And as we'll see in a moment, there's a balance between the attractive force of the bond and, when atoms get too close together, what's at the center of each atom? A positively charged nucleus. Positive charges don't like being close together. So there's going to be a trade-off between the attractive force of the chemical bond and the repulsion of the positively charged nuclei when they get too close together. So we're going to take a look at that in just a moment. All right, so we've got the chemical bond, and we've got a balance between the attraction that results from the stability gained, all right, and you've got this repulsion due to the nuclei getting too close together. Let me remind you of a few things that we did in the last chapter in forming ions. And I'll use an example that you're all familiar with. When we want to make some table salt, we take some sodium. So here's some solid sodium. And we'll mix that with some chlorine gas. And as you'll see soon enough, chlorine, when it exists in nature as a gas, it's actually two atoms of chlorine bonded together. So that's Cl2 gas. And when these combine, we make table salt, NaCl. Okay. Now, just like we did in the last chapter, we need to make sure we're obeying the law of conservation of mass. And you've been doing this a lot now in lab. You've been seeing balanced equations. So let's go ahead and balance this one. We have 2 chlorine atoms on the left, and I only have 1 chlorine on the right. So if I put a 2 coefficient here, now I have the chlorines are balanced, but now that gives me 2 sodiums on the right. I need 2 sodiums on the left. There, now I have a balanced equation. I'm obeying the law of conservation of mass. Now we know what happens with sodium. Sodium has that 1 electron in the valence shell, right? So if I were to draw or describe, here's 2 sodium atoms, and if it can lose those electrons, it will. And when it does, we're going to end up with 2 sodium ions. We already know what that looks like. We described it. We're not going to do the electron configuration and orbital diagrams for that anymore. But now I'm going to show you that in the context of here are the 2 electrons that were lost. Now, when we did this last chapter, I told you that they don't just lose electrons to thin air. It takes energy to get those electrons to leave the atom, the ionization energy. So this will only happen if there's something else that it's reacting with that's going to want to gain those electrons. And here we have some chlorine gas. Chlorine, as you know, is 1 away from being full valence shell. So it wants to get electrons if it can. So let's write another reaction that describes the chlorine. Each one of those atoms wants to gain how many electrons? 1, but we have 2 of them. So we need 2 electrons to be gained here. And when we do that, we'll form 2 chloride ions. Now that's part of the naming. It was chlorine as an atom, and now I'm calling it the chloride ion. But you'll learn all about that naming when you study that on your own. IDE, chloride ions. All right, now if I consider both of these together as one reaction, okay, things will cancel out. We've got 2 electrons on this side of the reaction arrow, will cancel out with those 2 electrons. So it's like math if we consider the reaction arrow being an equal sign. Okay, and then let's write down everything that we have that remains. We've got 2 sodiums plus 1 Cl2 will give us 2 sodium cations and 2 chloride anions. And of course, if I merge them together in an ionic bond to form sodium chloride, we have the reaction that we started with. I just split it up into the 2 parts. Okay, that's actually a preview for what we're going to be doing later on in the class when we get to something called oxidation and reduction reactions, the gain and loss of electrons. But that's coming later. I don't want to bring that up now. But now let's just look at these 2 ions that we formed. The ions that are formed, do you understand why that happens? It's all driven by the stability gained by them attaining an isoelectronic electron configuration with their nearest noble gas. So here we have a sodium, you can't maybe see it on your slide. So that's a positively charged cation, and here's a negatively charged anion. Okay? Now, on this graph, we've got distance on the x-axis. It's not labeled. So this is going to be our distance between the nuclei. And we don't need to put a scale on here. This is just going to be a relative distance. When we start far apart, we formed the ions already, right? That's a separate issue. They formed, we know why they formed. Once they're formed, we know that positive and negative attract each other. But we're going to start with them far away where there's no interaction, okay? And as they become closer and closer, so as the distance between the nuclei gets shorter, so now I'm moving towards the left, okay? We're going to see that we're going to gain some stability. And we're going to measure that by this electrostatic potential energy that's shown on the y-axis. So as you go below the line there, we're getting more stable. And as we go above the line, we're getting less stable. All right. So what I want to do is have you guys start discussing with your neighbors. All right. You've all got this slide in front of you. And let me just label 3 separate regions here. Here's region A, region B, and then there's this dashed line here. Let's call that C. All right. So turn to your neighbor, say, hey, how you doing? My name is, if you don't know your neighbor yet. You can talk about how the exam went, how you feel. Right? But then discuss, what do you think is going on in A, B, and C? When you're trying to look at a graph like this, what kind of information is it telling you, right? And it's okay if you don't have the right answer yet, because we're just starting this discussion. This is just designed to help get your brain in the mood of what we're going to be discussing today and for the rest of the week, okay? So turn to your neighbor, spend a couple of minutes discussing, see if you can decide what's happening in A, what's happening in B, and what does that line C represent? All right, I heard some good ideas when I was wandering around there. I heard some things like ionization energy, stability, and all sorts of good stuff. So who thinks they know what's happening in A from your discussions? Just shout it out. Say what? The energy is going down. But what does that mean, the energy is going down? We're getting more stable, right? The electrostatic potential energy is going down. So the more stable things are, the lower it's going to be on this graph, okay? So as we're getting these ions close together, okay, we start with them so far apart that there's no interaction. So the electrostatic potential energy here is 0. But as they get closer together, look what's happening. Here, I'll trace this in red. As they get closer together, it's becoming more stable, it being the products, all right? The product is by these ions coming together, right? The positive and negative are coming closer together, they're stabilizing each other. So overall, it's a lower potential energy. But at some point, this curve goes back up. We go from here. So let's define what A is. We're gaining stability here. This is electrostatic attraction. Okay, but then what happens when we pass this point C and start going back up here? What's happening? What's happening in region B? Go ahead.
I think it's because.
Yeah, that's what I said at the beginning. Yeah, now we're getting them so close together because they're stable that way. But now they get so close together that there's that positively charged repulsion is now taking over because you're bringing the positively charged nuclei too close together. So in the region B here, this is now repulsion. And that's due to the positively charged nuclei getting too close to each other. Now, obviously, that's going to differ depending on what the two ions are, okay? Because as you also know, different ions have different sizes. We discussed that and those trends last time as well, okay? So where that curve starts to go back up again is going to be dependent on what the two ions are that we're talking about. But what's happening here at C? We're at the bottom of that curve. What does C represent to you? The most stable, right? Certainly that's true. And if we're to the right of C, well, there's still some more stability to be gained, right? And if we go too far to the left of C, now that repulsion is taking over, so it's going to push it back the other way. So if we're talking about the distance, okay, because that's what we're measuring on the x-axis here. So if this is the most stable, what distance do you suppose that would give us? It's a bond distance. We can measure this. That's going to be that most stable position. That's the trade-off. That's the balancing act between the stability gained opposed by the repulsion due to them being so close together. And you can actually measure this. Usually we're measuring this in picometers. And pico is 10 to the minus 12 meters, by the way. So that's really, really tiny, but you can measure it. Sometimes this is also called the bond length. We use those terms interchangeably. Okay. So this exercise was just designed to get your brain aligned with this concept, rather than us just drawing little models, all right, of how we think that these atoms are interacting in compound. It's really doing it because of this stability argument. And later on, we'll be talking about different kinds of bonds that we can form, because we'll be talking about single bonds and double bonds and triple bonds, all right? And those are going to happen. When they happen, they're going to define a different amount of stability gained when those electrons are being shared. And that's going to result in a different bond distance depending on how many are being shared and how close together those atoms can be before the repulsive forces take over. Okay. Now this was for ionic bonds. So let's stay on the topic of ionic bonding here. So just to summarize some of the things that I already told you to get to this point, right? We form the ions. That's due to the stability gained by becoming isoelectronic with its nearest noble gas configuration. And that happens by either losing electrons or gaining electrons. When we form ionic bonds, it's actually a two-step process. Actually, the ionic bond here is a two-step process. And we've already discussed them, but let me just define them formally for you. The first step is we're forming the ions. And we already know how that happens. That's what we discussed last chapter. Once we form those ions, then we have the attractive force due to the electrostatic attraction. All right, but just to remind you, this stability, this is what we talked about last time. This is when it becomes isoelectronic with its nearest noble gas. That's the driving force, really, of all ionic bonding. You won't get an ionic bond if you don't have ions. Why do you get ions? This is why. So really, when you form an ionic bond, it's step one. This is the real driving force. All right, now let's overlay onto this some terms that you've already learned, right? When an atom loses electrons, what do we end up with? We end up with cations. And what's the charge on a cation? Positively charged. These are called cations. And what kind of an element will lose electrons to form cations? Metals, nonmetals, metalloids? Metals. Okay, good. Right, and what types of atoms will gain electrons? And when they do, what do they become? Right, negatively charged anions. And what type of element forms negatively charged anions? Nonmetals. So just like in our example with sodium chloride, sodium is a metal. Chlorine is a nonmetal, right? That's exactly what we just did. Okay. In fact, here's some table salt for you right here. Now we describe this as NaCl. This is how we write it. This is NaCl. This is not a molecule of NaCl. This is a formula unit. And here is our definition of the formula unit. It's the ratio of the cations to anions that give you a net neutral pairing. You're always going to have a cation anion pair, okay? When you figure out what the formula unit is, it's really the lowest integer ratio. I should put that in here as well. It's the lowest integer. Ratio. So for sodium chloride, what's the ratio of sodium ions to chloride ions? It's 1:1. You can see that right there in the formula unit. Now, when there's a 1, you don't write the 1, okay? So you look at this, and that tells you that when you have a whole collection of salt crystals like this, it's not a molecule, but we have the formula unit. If we were to take our molecular tweezers and count all of the ions that were present in that bunch of salt, all right, we would find that there is the same number of sodium cations as there are chloride anions. They're present in a 1-to-1 ratio within this much larger crystalline lattice. All right, so this is all within a larger crystalline lattice or crystalline array. And you can see that we don't just have one sodium ion interacting with one chloride ion. In fact, there's a whole bunch. If I have the sodium ions written, well, you can kind of see it. Here's a sodium ion. Let's say those are purple. Any one sodium ion is actually surrounded by many, it turns out to be about 6 chloride ions. And I should really formally put charges on all of these because these are in fact ions here. And they're held together in this crystalline lattice, this crystalline array, due to the electrostatic attractive forces. But it's not just 1-to-1. The ratio is 1-to-1 within this much larger array. Now, how you come up with those formula units, it's actually quite straightforward, but it might be kind of tricky to you if you've never seen this before. So there's a couple of steps for you to do, and you know how to do them already, but let me tie them together for you. The first thing you want to do is recognize what are the charges that will result when they gain and lose electrons. Right? You already know how to do that because we did that last time. You had some exam questions on that. So for example, you look at sodium, you find it on the periodic table, you know it's got 1 valence electron, it will lose that 1 electron to become a 1+ cation. Okay, so first step is to recognize the charges that the ions will have. And then the second step, and this is going to be the one that's new to you, we need to find the ratios of the cations and anions so that the pairing is net neutral. So find the ratio so that the net charge equals 0. Okay, because we want a net neutral cation-anion pair. That's what we're looking for. Let me just remind you, these are not molecules. They're formula units. All right, so we know what that pairing looks like for sodium chloride, NaCl. We know that there's a 1-to-1 ratio of sodium cations and chloride anions. But there's all sorts of other ionic compounds out there that you'll see. Like here's one, here's calcium chloride. When I write calcium chloride properly, that tells me that the ratio is 1-to-2. There's one calcium cation for every 2 chloride anions. You see that? And calcium, you find calcium on the periodic table, it's got 2 valence electrons. So if it can, it will lose 2 electrons to become the calcium 2+ cation. And we already know that chlorine will gain 1 to form the chloride 1- anion. And so that's the ratio that they combine to give us a net neutral pairing. There's 3 things there. There's 3 total ions, but it's still a cation-anion pair. Right? But here we have 3 ions total. Here's aluminum oxide, Al2O3. How many ions are there total? There's 5, right? There's 2 ions that come from the aluminum, and there's 3 anions that are oxide anions. They combine in a 2-to-3 ratio to give us a net neutral pairing. Aluminum, you look that up on the periodic table, that's 3+. And the oxide anions are 2-. Now you might be able to just look at that, stare at that and say, well, I know this needs to be net neutral. Let me write that clear. I know this needs to be neutral. So how many of the cation do I need to mix with how many of the anions so that that neutralizes out? You might be able to just look at that and see, whoa, I need 2 of the aluminums and 3 of the oxides. But I'll show you a more formal way to do that right now. Maybe these are just some examples of the kinds of ionic compounds that we can describe. All right, so let's practice these steps now. And I'll show you some ways that you can determine how to get the net neutral ratio. So here are the 2 steps written for you again. And let's use an example. Let's say I give you some magnesium and some bromine. So let's do step 1, magnesium. What kind of ions do we form with magnesium? Here it is. Here's magnesium. Is it going to gain or lose electrons to become isoelectronic with its nearest noble gas? Lose. And how many? It loses 2. What noble gas does it become isoelectronic with when it loses 2 electrons? Neon. Very good. So magnesium, if it can, is going to lose 2 electrons and become the magnesium 2+ cation. All right. There, I'm showing it to you like this, like we did on the previous slide. What's bromine going to do? It's going to gain what? How many? It's going to gain 1 because bromine is a halogen. All right. It only needs 1 more to fill its valence shell and become isoelectronic with? No, not argon. This is bromine. Krypton. So bromine is going to gain an electron. Whoops, that's 2. I didn't balance the reaction, so that's okay. Bromine is going to gain an electron and become the bromide ion. But now we have our ions. This is the first step. We know that when we have ions, we're going to have magnesium 2+ and bromine 1-. So now there's 2 ways that we can come up with the net neutral charge. But I'm starting with an easy one because I think you can just look at this and already figure out what the net neutral pairing is. But let me show you formally how you do it. The first way, and really this is the formal way of doing it, is by using the least common multiple. So we need to find the multiples of each one and then go with the lowest one. So multiples of 1 are 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, blah. Multiples of 2 are 2, 4, 6, 8, 10, 12. So the lowest multiple between 1 and 2 is 2. Okay, so that means in this case 2. So we need to have 2 negative charges and 2 positive charges from these cations and anions. And that's what we're working towards. So how many magnesium atoms, sorry, how many magnesium ions do we need to get to 2+? Just 1. So we need 1 of those. And how many chloride, sorry, this isn't chlorine. How many bromide ions do we need to get to 2-? 2. So there you go. So 1 magnesium ion, that gives us 2+, and 2 bromide anions gives us 2-. So that gives us our net neutral pairing. Now we always list in an ionic compound, right? We always list cations first and anions second. This is just part of the nomenclature rules that you'll learn about on your own. So when we do that, we're going to list the cation first, that's Mg, and we're going to list the anion second, Br, and now we're going to put our subscripts in to show what the ratio is for the lowest, for the net neutral pairing. That's going to be MgBr2. And then what we call it, and again, the rules for how we name these things, you'll read about. This is called magnesium bromide. You'll learn that for some compounds, in some cases, you're going to remove the suffix of what the element name is and replace it with IDE. Okay? Now that's the formal way to do it. The second way to do this is a shortcut. And once you understand what the shortcut is shorting, it makes sense. I don't have a problem with you using shortcuts, but I do want you to understand what is the process that you're shortcutting. The shortcut is sometimes called the crisscross method, but it really uses the same skills. It's recognizing that, well, the cation is a 2+ charge and the anion is a 1- charge. And if I remember that I always write cation first and anion second, then the crisscross is simply you take the number of charges from the cation, and that's going to tell you the number of anions that you have. And then you take the number of charges on the anion, and that will tell you, here, I'll put a 1 here, even though we don't usually put a 1. Okay? And it works just fine. But really all you're doing is shortcutting, doing the least common multiple. And then the rest is just variations on this theme. So let me give you another example to work with here. And I already showed you what the result of this one was, but let me take you through it. Let's say I gave you some aluminum, and we're going to mix it with oxygen. Okay, so step 1, we already know what cation is formed from aluminum or oxygen. What is it? It's aluminum is the cation. What's the charge on the aluminum cation? Look at the periodic table if you don't remember. It's 3+, right? You already learned how to use the periodic table. You don't need to memorize these. You just need to know how to use the periodic table to get the answer. And you'll always have a periodic table in front of you on an exam to do this with, okay? So you should know how to look for any of these elements, especially if it's a main group element, all right? For the transition metals, you can't predict it easily, so don't worry about those. But for the main group elements, you should be able to look at its position on the periodic table and deduce what the charge would be if it formed an ion. So aluminum is 3+. The oxygen, when it forms an anion, what's the charge? 2-, because it only needs 2 electrons to get to its full valence shell. Okay, so we can do this by the lowest common multiple method. So what's the lowest common multiple between 2 and 3? It's 6. Right? 3, 6, 9, 12, 2, 4, 6, 8. So 6 is the lowest multiple that's in common to both of them. So we need to work for 6 positive charges and 6 negative charges. So the positive charges all come from the aluminum cation, and they come in packets of 3. You can't split them up. So how many aluminum 3+ does it take to give us 6+? It takes 2 of them. And how many oxide ions does it take to give us 6-? It takes 3 of them. So there you go, 6-. And so then we write it as cation first, anion second, and now we fill in our answer. We have 2 aluminums for every 3 oxygens. That's our formula unit for aluminum oxide. If you want to do it by crisscross, you still need to know what the starting ion charges are. All right, 3+ and 2-. Then you write down cation first, anion second, and then we do the crisscross. The 3 goes over here, and the 2 goes there. Okay? And really, that's as complicated as it gets. Because as you'll see when we get to covalent bonding, we're not going to form ions with 4+ and 4-. Those elements are going to form covalent bonds. So that's coming soon to a lecture near you on Friday. All right, but it can get more complicated, though, when we start using polyatomic ions. So that's what we're going to do now. But the math, the process is exactly the same. So what we've been working with right here, these are all monoatomic or monatomic. Sometimes when you have 2 vowels together, we drop one of them. These are all monatomic ions. They're ions formed from an atom that loses or gains electrons. You've been learning a little bit about polyatomic ions in lab. At least you've been using them in lab. So this will be your first of many times you're going to see a definition of polyatomic ions. They're no different from monatomic ions, except that they're from molecules, they're not from atoms. They're simply molecular ions. They're not atomic ions. We'll have a molecule of something. And you're going to learn soon enough in this chapter that molecules are covalently bonded atoms to make a compound. So when you have a polyatomic ion, it's simply a molecule consisting of many atoms, but overall, for it to be stable in nature, it has too many or too few electrons relative to the protons that it has collectively in all of those atoms, right? But it's the same thing. It's just on a slightly larger scale. And we're going to treat them the same way. Now, you've seen some of these in lab already. Let's see, what lab have you done? You've done, you did the flame test one that had nitrates in it. Remember the NO3 minus? That was a polyatomic ion. NO3 minus. This is called the nitrate ion. It's actually a molecule of 1 nitrogen and 3 oxygens that are bonded to each other. But overall, there's 1 more electron than we have total number of protons. So overall, it has a net 1 minus charge. You'll also be using in lab coming up soon the sulfate ion, SO4, and that has a 2 minus charge. You'll be seeing something else from time to time. Not all of these are negatively charged. Here's one that has a positive charge. This is called the ammonium ion. Okay, these are all molecular ions. I don't need to write it down again. There's a nice definition for you. They're covalently bonded. They have more or fewer electrons overall. And I should just put a little add to this. Overall, this is relative to the total number of protons. Because that's the positive charge, right? So here's an example. You'll be using this in lab soon enough. This is what we call copper 2 sulfate. Copper 2 sulfate, written, looks like this. It looks really complicated, but it's not copper sulfur tetroxide. It's copper 2 sulfate, and you'll be learning the naming of that and what it means. This is an ionic compound. If we put this in aqueous solution, we'll find, now what does AQ mean? Who remembers what AQ stands for? It stands for aqueous solution, but what does that mean? It's dissolved in water. The liquid specifically is water. AQ means dissolved in water. So if I were to write copper 2 sulfate like this in aqueous solution, that's really a shorthand. What it really means is that when we have this in H2O, they're separate ions in aqueous solution. We have copper 2 plus ions in aqueous solution, and we have the sulfate 2 minus polyatomic ion in aqueous solution. Okay, but when this is in aqueous solution, the SO4 2 minus, the sulfate ion, it still stays as a polyatomic ion in solution. It's really not a mystery. Just treat it as one thing. The SO4 2 minus doesn't break apart further in aqueous solution. It stays as the sulfate ion. So CuSO4, this is our formula unit. This is the lowest integer ratio when you have copper 2 plus ions and sulfate 2 minus anions. It's that simple. If I gave you iron 3 chloride, iron 3 chloride would look like this. The Roman numeral 3 is telling you the charge state on iron. I told you that with transition metals, you can't always predict, looking at the periodic table, what the charge is going to be. That's where the Roman numerals come in to help you, and you'll be learning about that on your own, okay? But this is going to be iron, that's a 3 plus charge. And we're going to mix that with, how many chloride ions do you suppose we need for that to be net neutral? We need 3. So we're going to have 1 iron 3 plus combining with 3 chloride ions, and that's going to give us one formula unit of FeCl3. That's iron 3 chloride. Now, of course, these are all monatomic ions, but let's look at iron 3 nitrate instead. It's the same deal, but now we're going polyatomic. So we've got iron, it's still the 3 plus cation, but now we're mixing it with the nitrate polyatomic ion, NO3 minus. So how many nitrate ions do we need for every iron 3 plus? We need 3. It's the same thing. But now when we describe the formula unit, we need to be a little careful here because it's iron and then we have 3 nitrates. So the way we show that is we put parentheses around the anion and we say subscript 3 because there are 3 nitrate polyatomic ions for every 1 iron 3 plus cation. Now, if there's just one, you don't need to put the parentheses. So like with copper sulfate, there was only 1 sulfate ion. So I could have put parentheses around it, but because it's just one, we don't do that. So you do have to get used to recognizing your polyatomic ions. I do try to use the same ones over and over again, both in lab and in lecture, so you get used to seeing them, right? So like sulfate, the nitrate, and ammonium ion, you're going to be seeing these a lot, and others as well. Okay, but this is the formal way we use the parentheses to group the polyatomic ions when you have more than one of them. And that's more than one polyatomic. If it's monatomic, so you don't need the parentheses for that at all. All right, so let's end with one that might look familiar, but maybe not. Let's give you a little more challenging one. Here's aluminum sulfate. Now, aluminum is not a transition metal, so I don't need to specify what the charge state of the aluminum cation is, because you look at the periodic table, it's a mean group element. So there's only one charge it can form. We only use the Roman numerals to differentiate what the charge state is when more than one can form. And again, you'll learn that on your own. So here's aluminum sulfate. We know that aluminum is a 3 plus and sulfate is SO4 2 minus. Okay, so what are we going to do? Cation first, anion second, SO4. Now notice when I write the formula unit, I'm not putting the charges in. Okay, I'm only putting the charges in when I'm describing the ions. But if I'm putting the formula unit in, that is by definition net neutral. So you don't show the charges in the formula unit. So we're just going to go crisscross. There's a 2 minus here, so we put a 2 here. There's a 3 plus here, so we put the 3 there. And that's the formula unit for aluminum sulfate. We need to put a 3 here because there's 3 sulfate ions for every 2 aluminum cations, but you don't show the charges. In the formula unit. And you may recognize now, that's the same combination as we had up here with aluminum oxide. Oxide is a 2 minus. Sulfate is a 2 minus. So the combination for net neutral is exactly the same. It just looks more complicated because we're describing it with a polyatomic ion.